I hope the screen is visible.
Yes, ma'am.
Okay. So today we are going to start a new topic. In fact, a new section altogether of this course that deals with the electronic circuits. So the primary difference that you will see in the circuits that we studied earlier with respect to the circuits that we are going to study now is the inclusion of non-linear elements. What are these non-linear elements? Non-linear elements are those elements where V directly proportional to I relationship is no more valid. So typical examples of these type of elements are the diodes, the transistors, and the operational amplifiers. The simplest of all is the diodes, with which we are going to begin this section. But before we start the diodes, let us actually see how the diodes are made in order to have a proper understanding of how they are going to function when certain voltages applied across these devices. Okay. So again, we know that the electric circuits, they are typically made of materials that we can broadly classify under three categories. So these could be the conductors or the semiconductors or the insulators. And this classification is actually based on their ability to conduct the electricity through them. So in case of conductors, the conductivity is very high or the resistivity is very low. So for example, if you talk about metals, good conductor metals are generally copper or maybe silver or sometimes aluminum. So these elements, they have very high value of conductivity, sometimes on the order of 10 to the power 8 free electron density. If you talk about insulators, then insulators are those material that do not conduct the electricity at all. So here the conductivity is very low, typically on the order of 10 to the power 8 to 10 to the power 10. And in between the conductivity of the conductors and the conductivity of the insulator lies the conductivity of the semiconductors. So although we have to now narrow down to the semiconductors, but before we do that, let us first do a recap of the concept of conductors that we already know. So if you may recall, for a conductor, if I say how to define a conductor, then we can say that conductor is a material that is typically characterized by flow of valence electron from their outermost shell. So here you have a diagram which shows the crystal structure for a metal. So generally those materials that have one valence electron or two valence electron in their outermost shell come under the category of conductors. So there you have one or two extra electrons which can move from here and there, thereby contributing to the flow of electric current. Now, if no external electric field is supplied, then what happens is that this flow of electrons or the motion of electrons inside this crystal of a metal is random. So this can move anywhere. Similarly, other electrons also, they tend to move anywhere. So if there is no electric field applied across this element, which is the conductor, then you have zero average current. Then in that case, we have zero average current. But what will happen if I apply some electric field? So if I apply certain electric field, then what happens? These electrons, they start aligning in a particular direction depending upon the polarity of the applied voltage. So what they will try to do, they will try to move to one of the extremes of the conducting material, and then because of this applied electric voltage and this alignment of the electron that is created, you develop an electric field across the metal. This electric field, we talk in terms of volts per meter. So you applied the voltage, certain alignment of electrons is created, and this alignment of electron leads to the formation of electric field. Then what happens is this electric field exerts some kind of force on these electrons, which cause them to move from low potential to high potential. So suppose you had this type of voltage connected. So here you have high potential, here you have low potential. So inside the conductor, what will happen? The movement of these electrons will be from low potential to high potential under the effect of force of this electric field. So that's how in the outer circuit, the current will flow from positive terminal to the negative terminal. This we already know. So one term that I would like to mention over here is the drift velocity U. So under the effect of this electric field, the electrons are going to move from the region of low potential to the region of high potential with a speed that we call as the drift speed U. So now we have a new term. This is U, and we call this U as the drift speed. So one thing here we need to mark is that the drift speed U is actually directly proportional to the electric field which is created. And this is intuitive also, because larger the electric field created, more force it will exert on the electrons. And when it will exert more force, the electrons are obviously going to move with high velocity. So in that case, we can say that the drift speed U is directly proportional to E. So now in order to remove this sign of proportionality, we introduce a constant. And that constant is denoted by mu. So don't get confused. This is U and this is mu. So now we say that U is equal to mu into E, where mu is known as mobility of the electron. Mobility of the electron, and it's measured in the units of meter square per volt second. So this is the very basic law that holds for a metal. In fact, this is the basis of the Ohm's law. Later on, I mean, not in this chapter, but in other courses, when you study these in a more detailed fashion, there you will see that this is actually the basis of the Ohm's law. Okay, so this is the first term that we learned, that's the drift speed. Now there is one more parameter of interest that I want to see in this case is the current density. The current density is denoted by J, and as we all know, this is current per unit area. So in case of metals, how can I calculate this? So say for example, I have a metallic strip like this, and it has length L and some cross-sectional area A. Then by applying electric field, what happens? The electrons, they start moving from this end to this end so that the net current flows from here to here. And let me say that capital N be the total number of free electrons in this cross-sectional area A. So now we know that the movement of electrons from one region to another region is going to create some current flow in this conductor. And what is my current? Current is actually given as the rate of flow of charge. So what is the net charge that is flowing? I have n number of free electrons. Each electron has a charge q. So the total charge is nq. And say it takes time t to travel from one end to other end, then I can say that my current will be given by nq by t. Up further, we know how much distance this electron is going to cover. This is going to cover distance L, and also it has speed u. So then from the principles of speed, distance and time, I can say that this time that the electron takes to move from one end to another with drift speed u will be given by t is equal to L by u. So if you substitute this back, what happens? I becomes equal to nq. Instead of t, I put L by u. So this is equal to actually nq u by L. So this is one way of expressing the current. What about the current density? Since J is equal to I by A, so this will be equal to capital N into Q into U divided by L multiplied by A. Now, in order to find out the value of capital N, this is a bit difficult task because you cannot count individual electrons present in a particular cross-sectional area. So what we do is we group this term together, N divided by L into A. So N is the number of free electrons, L was my length and A is my area. And I know that length into area gives me the volume. So this N divided by capital L plus A can be written as small n, which is the number of electrons present per unit volume. So this is number of electrons per unit volume, also known as free electron density of the material. So the formulas that you will generally use, and in the questions what will be given will not be capital N, but it will be small n, just for the reason that small n is easy to measure compared to capital N. ठीक है, तो यहाँ से for the metals the formula of J becomes small n Q multiplied by U, where small n is the free electron density, Q is the charge on one electron, and U is the drift speed. Further, if you want to substitute the value of drift speed, then this can also be written as NQ into mu into E, where mu is the mobility of the electron. E is the electric field. And this has a more popular term, NQU. This is sometimes called as sigma into E, where sigma is the conductivity of that material. Where sigma is the conductivity of that material. Okay? Sigma, the conductivity will be given by N into Q into mu. Now, given the conductivity, we know one more term, that is the resistivity, and it can be related to conductivity by the relation resistivity rho is equal to 1 by sigma. So this relation we already know. And one thing that we need to remember is that this conductivity is dependent upon the temperature. So if the temperature changes, the conductivity will change, the resistivity will change, and all other dependent values that we have calculated over here will change. So when we are talking about the calculation of any of these factors like the drift speed or the current density, we generally talk about at a particular temperature. Given the temperature is this, what is the value of current density or the drift speed or any other parameter? If there is a change in temperature, then you need to consider how the conductivity will change or how the resistivity will change. So that expression also you must have already studied, but just for the sake of completeness, I'm including this. So this change, the new conductivity, say this is the conductivity at temperature T. This will be equal to conductivity at a given temperature rho naught multiplied by 1 plus alpha times T minus T naught, where this is the gradient or temperature coefficient भी कहते हैं इसको sometimes. Okay, so now we have the formula for the conductivity and the current density in case of metals. So if I get back to the formula for the current, from the formula for current density, I can say that I is equal to J multiplied by A. You substitute the expression of J, this will be equal to sigma into E into A. So let me just multiply the numerator and the denominator by L and regroup this a bit. So this will become sigma into A divided by L multiplied by E into L. So this E was electric field, which was in terms of volt per meter. and this is the length of the conducting material. So this is in terms of meters. So this E into L product is actually the volt that you are applying across this conductor. So what I want to derive from here is a very trivial formula that you actually told me in the first class. This I will be equal to V into sigma A by L. So we have V by I, which is also equal to the resistance of that particular conductor. This will be given by L divided by sigma A, or this is equal to rho L by A. Okay, all these things you know already, but just for the sake of putting everything together, we are revising this. तो अभी तक हमने देखा in case of conductors, what is the typical structure of the lattice? Then there are free electrons, which results in the movement of charge. Then there is a term which we call as the drift speed, which relates to the mobility of the electrons. And then further we saw how the current density is calculated. Now we are going to move to another part, that is the semiconductors. So let's see what happens inside the semiconductor. So here in this figure over here, the crystal lattice for a semiconductor material is shown. So here we see that unlike the conductors, here the material has 4 electrons in the valence shell. So you have a single atom, and these single atoms are going to have 4 electrons in their outermost shell. So typical example of semiconducting materials are germanium and silicon, because these have 4 electrons in their valence shell. So what they do is these 4 electrons, they combine with the valence electron of the adjacent atom and forms the covalent bond. So in this case, what happens, because all the electrons form the covalent bond, the conductivity is very low, because due to the tightly packed arrangement of electrons in this lattice, there are not much free electrons to move from here and there. In fact, if you talk at very low temperatures, the semiconductors typically behave as insulators. But if you increase the temperature, for example, I'm talking about at room temperature. What happens at room temperature? Because of the presence of thermal energy, this covalent bond breaks. I mean, not all the covalent bonds will break, but at least some of the covalent bond will break. Some of the covalent bond break होगा तो क्या होगा? यहाँ से एक electron जो already एक covalent bond में था, this becomes a free electron. This comes out and becomes a free electron, leaving a hollow over here. So this hollow is called a hole. That means at room temperature, by absorbing the thermal energy, an electron hole pair is created. We will not just say that an electron is created, but rather we will say that an electron hole pair is created. So one hole is assumed to carry 1 unit positive charge. Okay, earlier you must have read about protons. Protons are the elements that carry positive charge, but actually protons are placed inside the nucleus, so it's difficult to cause the movement of protons and have some current because of the flow of positive charge. But here holes can be created in the outermost shell very easily because of the absence of electrons. So whenever there was an electron but that electron moved out, so we will say that the place from where the electron moved out, a hole is created, and this hole is assumed to carry 1 unit positive charge. ठीक है? तो यहाँ पे जो होल क्रिएट हुआ, अब इसके साथ क्या होता है कि some more valence electron may come from somewhere and fill this hole. So जहां से इलेक्ट्रॉन आके इस होल को फिल कर रहा है, वहां पे एक न्यू होल क्रिएट हो जाएगा. So we can say that this is equivalent to the hole being moved from location 1 to location 2. Similarly, location 2 पे जो hole create हुआ है, this can be filled by some valence electron coming from location 3, so that at location 3 a new hole is created. So this gives an impression that there is a flow of positive charge happening, and this phenomena we call as Hall current. Hall current, you can understand this as the flow of positive charge. Similarly, there will be the flow of electrons also. Obviously, because electrons free ho rahe hain, so they are free to move here and there. So in fact, there will be two currents inside the semiconductor, one because of the movement of holes and other because of the movement of electrons. So this is a very important difference between a metal and a semiconductor. In case of metals, we only talk about the flow of charge which pertains to electrons. That's why also sometimes you call the metals as unipolar devices. Whereas in case of semiconductors, you have a Hall current as well as you have the current due to the presence of electrons. So these two types of current makes semiconductors as bipolar metals, or bipolar, not bipolar metals, but bipolar materials. This is a very important difference. Then if I want to write the expression for J, that is the current density in case of semiconductors. So how can I write J? For metals, I said that J is equal to N into Q into mu into E, where everything was because of the presence of electrons. So let me say that this is mu N, or mobility of the electrons. This was for metals. If I talk about semiconductors, so since I know that semiconductors have two different type of charge carriers, one positive and one negative, so J will be the contribution of both of these elements. So in this case, I will say that J is equal to small n into mu n into Q into E plus small p into mu p into Q into E. So just as small n was free electron concentration, small p will be the Hall concentration. Mu n was the mobility of electrons, mu p is the mobility of holes. And Q we know this is 1 unit positive charge, and E also we know this is the electric field. So in case of semiconductors, the expression for current density gets modified in this manner. Now one more, yeah.
Ma'am, for the movement of holes, like why does some other electron specifically occupy that hole and not go into some other place?
हाँ, कोई अदर होल में भी जा सकता है, कोई अदर होल में भी जा सकता है, तो यहाँ पे भी तो कोई आएगा, right?
No, I mean, can it not be like all electrons are just leaving their places but not occupying some other hole?
No, this does not happen. This does not happen because negatives tend to attract a positive thing. So if there is nothing over here, we assume that there is some positive charge. So this is going to attract any negative charge which is nearby. So it's not that there is a hollow which is remaining or baki electrons are just floating around. Understand?
Yes.
ठीक है. Okay, so we defined J, that was the current density for the semiconductor. Now, one more very important point that I want you to keep in mind is that in case of an intrinsic semiconductor, now what is intrinsic semiconductor? This is a pure semiconductor. Why I am calling this as pure, this you will understand in a while, क्योंकि थोड़ी देर बाद हम semiconductor में impurities add करेंगे. So for now, you assume that inside the semiconductor crystal, we have atoms only of that semiconductor and not of any other elements. So for such pure semiconductors, also called as intrinsic semiconductors, the concentration, free electron concentration, is always equal to the Hall concentration, and this is equal to Ni, which is the intrinsic carrier concentration. We call this as intrinsic carrier concentration. And this intrinsic carrier concentration is actually the property of the material. What do I mean by that? So we said that, okay, there can be two typical examples of semiconductors. These are germanium and silicon. So for germanium, Ni will have some different value, and for silicon, Ni will have some different value. So what actually happens is when the electron is in a covalent band, I mean when it is in a covalent bond, then the electron is present in the valence band. ये इलेक्ट्रॉन अभी यहाँ पे है, जब ये किसी के साथ कोवेलेंट बॉन्ड में बंधा होता है, then we say that the electron actually resides in the valence band. Then when you increase the temperature, what happens is that this electron absorbs the energy from the temperature, the thermal energy, and it jumps from the valence band to the conduction band. तो अब इलेक्ट्रॉन जो पहले यहाँ पे था, वो इलेक्ट्रॉन अब कंडक्शन बैंड में आ जाता है, leaving behind a hole over here. So actually free electrons are present in the conduction band and holes are present in the valence band. तो कितने electrons यहाँ से यहाँ जाएंगे? This will depend upon what is the energy gap between these two bands, that is the conduction band and the valence band. And different materials like germanium, silicon, they have different values of energy band gap, which is the property of that material. So therefore, I say that this is something which is very specific to a given material, but if you have an intrinsic semiconductor, then the concentration of free electrons will always be equal to the concentration of holes, and we call this as the intrinsic carrier concentration. So this is the thing that you should remember, that N is equal to P is equal to Ni. Now what we do is we add some impurities to the semiconductor. तो अब impurities क्यों add करनी है यहाँ पे? तो अभी just now what we saw that if I want to increase the conductivity of the semiconductor, what I could do is I can increase the temperature. Because at low temperature, we know that semiconductor is going to behave as an insulator. But if you raise the temperature, say if you bring them at room temperature, then covalent bond टूट जाता है, electron hole, everything, and then some current flows, जो हमने अभी देखा. But increasing the temperature always is not a good thing, because we know that if I increase the temperature, the property of the material may change. Resistivity change हो सकती है, conductivity change हो सकती है, current density change हो सकती है, many things can change. So increasing the conductivity of the semiconductor material by increasing the temperature is generally not a good idea. So in that case, what we do is instead of increasing the temperature, we add impurities to the semiconductor material. Why I'm calling this as impurity? Because this is not the same material as the semiconductor itself. So this will be some other material. What are these impurities and how does this increase the conductivity is what we are going to see. So first thing is, what are these impurities? So अभी हमने बोला कि by the addition of impurities, I'm going to increase the conductivity of the semiconductor material. This process is known as doping. And the resultant semiconductor which is formed is known as a doped semiconductor. Doped semiconductor is also sometimes called as the extrinsic semiconductor. Okay, now the impurities that are added are generally of two types. The first type of impurity is known as a donor type of impurity. These donor type impurities are those materials that have 5 valence electrons in their outermost shell. So what can be the example of these type of impurities? It could be phosphorus, it could be arsenic. These are two typical examples that are used to create N-type semiconductors, or they behave as donor type impurities. So when you take such a material which has 5 valence electrons in their outermost shell, so what happens? Out of these 5, 4 electrons, they form covalent bond with the semiconductors, as you see over here. So say for example, this is an impurity atom. So this was an impurity atom. It had 5 electrons in the valence shell. So 4 electrons, 1, 2, 3, 4, they were used in the formation of the कोवेलेंट बॉन्ड और एक इलेक्ट्रॉन फ्री रह जाता है. So this free electron is kind of donated in order to carry the charge from one place to another. That's why we call this type of impurity as the donor type impurity. And the resultant semiconductor that is formed by including the donor type impurities is known as an N-type semiconductor. Why N-type? Because the free charge carriers are electrons and electrons carry negative charge. Therefore, this type of impurities form the N-type semiconductor. Now, another type of impurity that is used is the acceptor type impurities. What happens in acceptor type impurities? These are generally those materials that have 3 electrons in their valence shell. The typical examples that are used are boron and gallium. तो अब 3 electrons में क्या होता है कि जो semiconductor है, this has 4 electrons in their valence shell. So these 3 electrons will bond with 3 electrons of the semiconductor material. तो यहाँ पे एक इलेक्ट्रॉन बच जाएगा, which may form a covalent bond with some other valence electron of the semiconductor material itself. But here, because in the outermost shell, there were only 3 electrons, so we say that one excess hole is present. In fact, this is the absence of one electron because there were only 3 valence electrons. So 3 valence electrons means one electron was missing, but we don't say that here one electron is missing. Rather, we say that this is having 3 valence electron and one hole. So these valence electrons will be used in forming the covalent bond with the semiconductor material, and what remains behind is the hole which was belonging initially to this boron or gallium atom. And this hole which remains there in the crystal, this can accept any valence electron coming from somewhere else. So since this can accept the electrons, that's why these are known as the acceptor type of impurities. And therefore the resulting semiconductor, doped semiconductor that is formed is known as a p-type semiconductor. Why p-type? Because the net majority charge carrier is a hole, and hole, we assume that a hole is carrying a positive charge. So what we saw that in a semiconductor, if I add impurity, I can increase the conductivity. 2 types of impurities are there. If I use a donor type impurity, I will create an N-type semiconductor. If I use an acceptor type impurity, I will create a P-type semiconductor. Okay? One thing that you can keep in mind is that for N-type semiconductors, as we have already seen, the majority carriers are electrons. So if the majority carriers are electrons, then the free electron density is much, much greater than the hole concentration. And similarly, in the P type of material, because majority charge carriers are holes, therefore, in that case, we say that the hole concentration is much, much greater than the free electron density. So now said this, we will now see 2 basic laws which relate the total charge in a semiconductor material. So the first law over here is the mass action law. What this mass action law says that regardless of the amount of doping, the product of N and P will always be equal to Ni square. So earlier we have seen that for an intrinsic semiconductor, N was equal to P was equal to Ni. So obviously if you do N into P, this will be equal to Ni square. So this law is clear from here itself. But what is the change when you talk about the doped semiconductors? In doped semiconductors, we know that now N will not be equal to P. Either N will be much, much greater than P, or P will be much, much greater than N. But irrespective of the level of doping, at thermal equilibrium, this law will always hold. This law will always hold at thermal equilibrium. What do I mean by thermal equilibrium? That means throughout your semiconductor slab, और मान लो ये तुमने एक slab लिया है semiconductor का, तो इसमें throughout this slab the temperature is same. So if the temperature is same, then in that case the product of N and P will be equal to Ni square. This is the first law known as the mass action law. Then another important law which holds in general for the semiconductor material is that we know if we have a semiconductor slab and we have not applied any external voltage, so there is no external voltage. So in the absence of external voltage, this semiconductor material remains electrically neutral. ऐसा तो नहीं होता कि हम कोई semiconductor material को touch करें और उसमें कोई current flow हमको feel हो. So although you have some hole current, some electron current, but the net current inside this is zero. So despite of adding doping, despite of increasing the conductivity, in the absence of any external voltage, this semiconductor material has to be electrically neutral. So for this equation, Nd plus P is equal to Na plus N holds true. So what is this? This is the net positive charge inside the semiconductor material, and this is the net negative charge. P, you know, this was the whole concentration, and also, you know, this was the electron concentration. Now, what is Nd? Nd is actually concentration of donor atom. So we know that we added an impurity. So agar donor type impurity add kiya, so it is going to give away one electron. So once it gives away one electron, it becomes a positively charged ion. It becomes a positively charged ion. So although this is ion, positively charged ion, it is not responsible for carrying any current, but still it has some charge. So this contributes to the total charge of the semiconductor. Therefore, this positive charge plus this positive charge should always be equal to this negative charge plus this negative charge. Where what is Na? Na will be the concentration of acceptor atoms. So these are the two basic laws that relate the total charge in the semiconductor. First is the mass action law, and other is the law which says that the semiconductor will be electrically neutral in the absence of any external voltage. Now what happens for an N-type semiconductor? यहाँ पे हमने देखा कि N was much greater than P. So if you substitute this over here, if N becomes much greater than P, then I can simply write that in this case, Nd plus P will simply be equal to N. Because sorry, it's an N type of semiconductor, so you will not have any acceptor atoms. क्योंकि N type बनता ही donor type of impurities से है. So Na goes away. This is the first thing. And secondly, we also know that since N is much greater than P, therefore I can simply say that Nd will be approximately equal to small n. So if Nd is approximately equal to small n, I can find out the value of P, however small it may be, by using the mass action law. So this will be simply equal to Ni square divided by Nd. So these are the two things that can be useful while solving the questions. If I talk about the conductivity for N type of semiconductor, what will be the conductivity? Sigma N. This will be only due to the presence of the electron. So we can write this as N into mu N into Q. Similarly, for the case of P type, in the P type, we do not have Nd component because P type is formed by the concentration of acceptor type of atoms. So for P type, the equation will be Na plus N is equal to P. And again, we know that here P is much greater than N. That means I can simply say that Na is approximately same as P. And in this case, if I want to find out small n, howsoever small it may be, I can again use this formula. So this will be equal to Ni square divided by Na. How about the conductivity for P-type semiconductor? This will be sigma P equal to N ki jagah P, mu N ki jagah mu P, and Q remains as it is. ठीक है? Is it fine?
Yes, ma'am.
Okay. Now what happens? अभी तक हमने देखा कि if I had to have the movement of charge, अगर movement of charge करवाना था तो हमने क्या किया था कि इलेक्ट्रिक फील्ड लगाई थी. So we said that if I apply an electric field, they will exert force on the electrons and the electrons will start moving. This is one way of causing the flow of charge. Another way of causing the flow of charge is to have a non-uniform concentration, of charge carriers. So what do I mean by this? So initially what I assume that everywhere, if it's a doped semiconductor, then the constant, say if it's an N type of semiconductor, then the concentration of the electrons is uniform across this slab. But when I say that non-uniform concentration, that means if I assume that this is a reference point, say over here, if I assume that this is the reference point, then at different distances from the reference point, the concentration of N or P will be different. So let me say that this is reference and this is the distance X. So as you increase the value of X, the concentration of N or P will change. So in this case, what happens? You have a gradient which is defined by either dP by dx if it's a p-type semiconductor, or dN by dx if it's an n-type semiconductor. Here a gradient is formed. So what happens when you have non-uniform concentration? Then there is a tendency that charge automatically moves from a region of high gradient to a region of low gradient. Okay, first of all, understand that when you have non-uniform concentration, then at different distances in this slab, the concentration will be different. और अगर concentration अलग-अलग जगह अलग-अलग है, say here the concentration is small and here the concentration is large, then automatically by the tendency of the material, the charge carriers are going to move from the region of high concentration to the region of low concentration in order to attain equilibrium. Right? So this process wherein the charge carriers move from the region of high concentration to the region of low concentration in order to attain equilibrium is known as the process of diffusion. Okay? And because a gradient exists, we call this type of semiconductors as graded semiconductors. Okay? Any doubt? This dP by dx is also known as concentration gradient. Now let us try to see what will happen to the current density in case of the graded semiconductors. So let me first write the formula, then I'll try to explain what that means. So say I have a P type of semiconductor. So in a P type of semiconductor, the current density, let me denote this by Jp. This is given as Q multiplied by minus dP into the concentration gradient dP by dx. So what is this? This term which I wrote inside the bracket, this is actually the particle flux density, also denoted by phi p. You call this particle flux density. So not to scare you with many new terms, particle flux density क्या बताती है? It is simply the rate of transfer of charge. ठीक है? So we know that there is some movement of charge from the region of high concentration to the region of low concentration. So at which rate this movement is happening is denoted by this term phi t or particle flux density. Why minus over here? Minus is because the movement is from high region to low region. ऊपर से नीचे जा रहा है, कम हो रहा है, that's why you keep this minus. And this dp over here, this is known as the diffusion constant. Diffusion constant because it's p, so this is diffusion constant of hole. So the current density is actually the rate of transfer of charge multiplied by the total charge. I think now it would be clear. This is rate of transfer of charge. That means at what rate the charge was moving from high concentration to low concentration, and that multiplied by how much charge one carrier is having. This will give me the current density of p-type semiconductor. Similarly, for an n-type of semiconductor, this will be given by charge multiplied by the particle flux density for an n-type material. So this is given by minus dn into dn by dx. But here, since q itself is minus due to the presence of electrons or due to the presence of the negative charge, so Jn is actually positive in this case. This becomes q dn into dn by dx. So if there is no external applied electric field, then the current density will be given by the concentration gradient and the charge defined over here like Jp in this case and Jn in this case. In fact, ये जो diffusion constants होते हैं, dp and dn, they are also related to the mobility of the charge, which we have already seen. There is an equation which relates all of these. So this is like dn by mu n is always equal to dp by mu p, and this is given by k into t divided by q, also known as vt, where vt is the volt equivalent of temperature. Here k is your Boltzmann constant, T is the temperature in Kelvin, and Q is 1 unit charge. So diffusion, which is causing the movement of charge, is actually related to the mobility of the electron as well as hole by this particular relation. And this relation is also known as Einstein's equation. So this was in the case where you do not have any applied electric field. Now say if you have applied an electric field also. So remember, we are talking about the graded semiconductors. Graded semiconductor में अगर electric field लगाओगे तो there will be two components of the current density. One will be because of the concentration gradient and other will be because of the presence of electric field. So in that case, Jp will be given by the sum of both the components, that is n, P के लिए P होता है. This will be given by P into mu P into Q into E minus Q times dP small dP by dx. And how about Jn? This will be n into mu n into Q into E. This component is due to the presence of electric field, and this component is due to the presence of the gradient. So that is how we define the current density in a graded semiconductor in the presence of electric field. Then one more important relation is the relation which concerns to the mass action law. So we have already seen that mass action law states that for a given semiconductor, N into P is always equal to Ni square. Now in a graded semiconductor, what happens? Say at distance x1 from the reference point, you have the concentration as N1 and P1. And at distance x2, you have the concentration as N2 and P2. Then following the mass action law, N1 P1 will always be equal to N2 P2, and obviously this will be equal to Ni square. So this is the slight modification of the mass action law in case of graded semiconductors. Any doubts as of now? No doubt? Okay, so if there are no doubts, then I'll quickly cover one concept. It will take just 2-3 minutes and then we will close. So this is the concept of PN junction. So now what happens? Say we have two graded semiconductor types, एक P type semiconductor लिया और एक N type of semiconductor लिया, and out of that we created a slab, semiconductor slab, such that one side is the P type semiconductor and other side is the N type semiconductor. So then the boundary of this P type and N type semiconductor is known as a PN junction. Okay? So this PN junction has two important effects. This PN junction is actually the basis of a diode. Therefore, we are studying this PN junction over here. So first we studied what is the pure semiconductor. Then we studied by adding the impurities, you have doped semiconductors. Then doped semiconductors could be graded. And then when two different graded semiconductors come together, they form a PN junction as shown over here. So now what happens when this junction is formed? There are two effects. The first effect is the formation of barrier potential. The first effect is the formation of barrier potential. तो क्या होगा कि यहाँ पे concentration अलग है, यहाँ पे concentration अलग है. So this difference in concentration actually leads to the buildup of a small electric field, thereby creating some small potential over here, which we call as the barrier potential. And this is defined by this formula. We are not going to go into the derivation of this formula because this you will do in detail when you will study devices and materials in your upcoming semester. So as of now, you can just keep in mind that formation of a PN junction will cause some potential buildup at the junction. And this potential we call as the barrier potential, which is given by this formula. Okay? This is the first after effect. The second after effect is the formation of depletion region. Achha, one more point here, because of the presence of barrier potential, this is typically very low voltage. This is typically very low voltage and it does not cause the flow of any external current. Internal current तो नहीं होगा, क्यों नहीं होगा? This we will see in the next class. But because this is very low voltage, so because of this barrier voltage, there will not be any external current. And when actually you will apply some external battery to this PN junction diode, then this barrier potential becomes dissolved in order for the current to flow from here to here. So this concept also we will see in the next class. As of now, you can remember that this barrier potential is too small to cause any flow of electric current in the external circuit. Then the second concept is the concept of formation of depletion region. So what happens? In the PN junction, we have actually brought together a P-type semiconductor and an N-type semiconductor. So P-type semiconductor का जो crystal होता है, वो कैसा होता है? So you have, because P-type semiconductors are formed because of acceptor type of impurities, which have accepted an electron. So they carry a negative charge. So these are negatively charged ions, which are formed because of adding of acceptor type impurities. And then there are free holes. Similarly, in case of N-type semiconductors, you have a positively charged ion. This is formed because of the adding of donor type of impurities, because when donor type of impurities give away their electrons, they become positively charged ions. So these are ions, they are immobile, they will not contribute to the flow of charge, but still they are present. So inside the crystal, you have positively, negatively charged ions along with electrons and holes. So what happens in the region near the junction? Because you have positive and negative charges adjacent to each other, तो ये जो free flow charge carriers होते हैं, electrons and holes, they recombine with each other. So in the vicinity of this junction, you do not have any free charge carriers. Rather you can call this as free mobile charge carriers. And therefore, this region is known as the depletion region. So the idea was that when you form a PN junction, it will lead to two effects. The first effect is formation of barrier potential, and the next is the formation of depletion region. So in the next class, what we will see is how we can use this PN junction to create a diode, और फिर diode के क्रॉस जब पोटेंशियल लगाते हैं तो डिप्लीशन रीजन के थ्रू करंट कैसे फ्लो करता है. This is what we are going to see in the next class. So I'll stop over here. If there are any doubts, then you can please ask now.
Ma'am, what was Ni?
Ni is the intrinsic carrier concentration. So intrinsic carrier concentration means here. So intrinsic carrier concentration means when there are no impurities in the system at that time, at room temperature, what is the number of electrons or the number of holes that are flowing across in the conduction band or the valence band.
So it is either the positive charge density or the negative charge density.
Yes. So in case of pure semiconductors, since both of them are equal, so this could be anything. This could be anything. लेकिन अगर n type पे लूंगी तो ये ni की कुछ value होगी, which is actually experimentally measured and it is, I mean, listed across as the property of that material. So based on this, you can assume that this will be constant. So इसके basis पे for a graded semiconductor or for an extrinsic semiconductor, you can find out the value of n and the value of p.
So like even in a doped semiconductor, Np equal to Ni square, the Ni is intrinsic carrier density.
Yes, this is always the intrinsic carrier concentration.
Okay. Okay, ma'am.
ठीक है. जब जब सेमीकंडक्टर प्योर था तब n और p इक्वल थे, तो ऑब्वियसली n and p आर इक्वल, तो प्रोडक्ट ऑफ देम विल बी इक्वल टू ni स्क्वायर. जब मैंने डोपिंग कर दिया तो n विल बी मच ग्रेटर देन p, बट स्टिल दिस इक्वेशन विल होल्ड. ठीक है, बिकॉज यू कैन नॉट क्रिएट एनी एक्स्ट्रा एनर्जी, so always you will have to have some balance between them.
Okay, ma'am. Ma'am, and in the PN junction which we discussed, तो उसमें जो N type semiconductor लिया था and P type semiconductor लिया था, they individually तो uniform distribution था ना?
In this case?
Yes, ma'am.
No, this we assume that they are graded.
Okay.
This we assume that they are graded. So that means junction से जैसे जैसे दूर जाते जाओगे वैसे वैसे the concentration of N and P type of charge carriers will be different.
So like this is caused due to the difference in doping in different areas.
Yes, these are created by different ways of doping. तो जैसे ये स्टेप ग्रेडेड है, ऐसे ही डिफरेंट और भी मेथड्स होते हैं ग्रेड करने के, बट दिस इज द मोस्ट कॉमन मेथड व्हिच इज यूज्ड फॉर द क्रिएशन ऑफ पीएन जंक्शन. एंड व्हाई ग्रेडेड आर यूज्ड? जनरली बिकॉज दे असिस्ट इन द फ्लो ऑफ करंट. जब यहाँ पे एक्सटर्नल वोल्टेज अप्लाई करेंगे, देन इन दैट केस इफ यू आर यूजिंग अ ग्रेडेड टाइप ऑफ सेमीकंडक्टर्स, दे एड इन द फ्लो ऑफ करंट. दैट्स व्हाई वी डू नॉट यूज यूनिफॉर्म ग्रेडिंग, वी यूज नॉन यूनिफॉर्म ग्रेडिंग.
Okay, ma'am.
ठीक है, एनी अदर डाउट?
Ma'am, is N-type semiconductor does it have a negative charge or is it neutral?
N-type semiconductor, so in the absence of any external voltage, it has to be neutral.
But we say that it has excess of electrons.
So that is when if you have an N-type semiconductor, उस N-type semiconductor से आपने कोई device बनाया, and that device you connect, say you created a diode from this end. This is a PN junction. So what you can understand is N-type semiconductor में when you apply external voltage, then the current will be because of the flow of electrons. Current will also be because of the flow of holes, but the current due to the presence of electrons will be much more than the current which is generated due to the flow of holes. But this is only in the presence of any applied voltage. If you do not apply any external field, then whether it is N-type or it is P-type, it has to be electrically neutral.
But then it would mean that the actual number of electrons and holes are equal.
No, it does not mean that because you have this relation Na plus P is equal to Nd plus N. So this has to be satisfied. If this is equal to this, that does not mean that P is equal to N. It means that the sum of these two should be equal to sum of these two.
Okay.
ठीक है?
And ma'am, one more thing, in the graded semiconductor, there is one current due to the like different concentrations. But like, is that like does that current last for infinite time? Because like there must be some time when it has like come into equilibrium. So now this
Yes,
current.
yes. Yes, you are right. So because of grading, the current is not going to last for long. Like in graded semiconductors, stand alone, it is never used anywhere. So the purpose is to use it against application of certain external circuits so that the grading helps in the flow of electric current. तो ultimately उसमें grading की वजह से जो थोड़ा बहुत current flow होगा उससे तो हमें मतलब भी नहीं है उतना. ठीक है? It is
Okay.
just to understand how it's working.
Okay.
Okay. Any other doubt?
Ma'am, I had a doubt from last lecture. Can I ask?
हाँ पूछो.
इसमें एक पर्टिकुलर लेक्चर स्लाइड में डाउट था. If you could open that. Slide 10.
This one?
Yes, ma'am. Here in the bottom left corner, you wrote that RS square plus omega R square L square upon RS. Bottom left corner.
यहाँ पे?
Yes, ma'am. RS square plus omega square R L square upon RS.
Are you talking about this thing?
Yes, ma'am.
हाँ.
So you have equated it to L upon CRS. I didn't understand how did you get that.
जस्ट अ मिनट लेट मी रिकॉल. तो यहाँ पे हम डायनेमिक रेजिस्टेंस निकाल रहे थे. So we said that resistance in this case is equal to voltage into the admittance, and then IR is equal to V into this thing. ठीक है? So then V by R. हाँ, तो इसमें what you need to do is you need to substitute the value of omega square. Omega square is equal to 1 upon LC.
Yes, ma'am.
तो ये सब्स्टिट्यूट करके ये नहीं आ रहा क्या?
नहीं आ रहा मैम.
Let me see. This will be how much? RS divided by RS square plus 1 by LC into L square. So this and this will get cancelled. This will be RS into C divided by RS into C plus L.
RS square into C plus L, right?
ओ इसमें नहीं रखना था. इसमें रखना था. So this becomes RS square plus 1 upon LC into L square divided by RS. So L and L will get cancelled, and I will have RS square into C plus L divided by C into RS. ठीक है?
Yes, ma'am.
So your question is इससे ये कैसे आ गया?
Yes, ma'am.
I need to check this. Can I tell you this in the next class?
Okay, ma'am.
Yeah, I'll check this. Otherwise, What's your name? Let me see. I cannot see you talking.
Jainam.
Janam. ठीक है. तो either I'll clarify this in the next class, or if I find time, then I'll clarify this to you over mail before we have our next class. ठीक है?
Okay, ma'am. Thank you.
ठीक है. Okay. Thank you.